with operations on decimals. And we had talked already about addition and subtraction. And much to your wonderful surprise, you saw wonderful relations back to fractions, right? Remember how fabulous that was? Okay, no, you're not. But we did it anyway. Sorry, I didn't save the work inside here. We talked about addition and subtraction, and we also talked about multiplication. And that's the last one I think you're on, wasn't it? Okay. So we're on to this one where we're talking about division. And I want to talk a little bit, I know that these are, some of your notes are already in there. I want to talk a little bit about why some of the things are that you do and why they work. So one of the things with division, sort of the algorithm that you remember, looks something like this. You make the divisor a whole number by moving the decimal point, and then you divide like you did with whole numbers. So literally what that looks like is you would put the decimal with the 75 underneath the division sign, and the decimal with the 05 on the outside, and you want to turn what's on the outside, which is the divisor, into a whole number. And so what would you do? Okay, so you move it to the right, and if you move it 2 to the right here, you 2 to the right over here, and it just so happens that makes it a whole number underneath. Sometimes it happens, sometimes doesn't. And then you say to yourself, okay, now I'm dividing by 5. So how many times does 5 go into 7? 1 times 5 is, and I subtract 2, and I bring down my 5, and then I say 5 goes into 25. 5 times 5 is 25, and I'm done. So this answer is 15. Thank you. So this is the algorithm that you remember. Why does it work? Why in the world am I allowed to just move decimals around? Why can I change something that was a decimal back into a whole number? What's going on here? Well, I want to show you how that's actually happening with, what do you suppose?
Fractions.
I know, you're so excited, aren't you? All right, so this is what this actually means, right, as a fraction. If I were to write the division as a fraction instead, okay? Now, somebody probably somewhere along the way told you that you're not allowed, if you will, to have fractions and decimals all mixed up like this, and right now we do. So how are we going to change this so that I don't have any decimals within this fraction? What could I do?
Fraction.
You could do that. I'm going to do something a little bit different. Multiply by what? 100 would be nice, because if I multiplied 5.05, 500 by 100, what do we get on the denominator? 5. We do. What do I get in my numerator? 75. And we can then look and see why we're dividing 75 by 5, and it looks exactly like the division over here, doesn't it? And of course we get the same answer. So what we're really doing when we move decimal points is we're really multiplying by, in this case, 100. But in reality, we're multiplying by some power of 10. Every time you move a decimal point, what you're doing is multiplying or dividing, potentially, by a power of 10. Okay, so that's what's happening. Yes, Emily?
Could you show us an example of when it doesn't, like, that when you move the decimal over, it's not a whole number, like it's a little bit?
Yeah, we could use the same values here, and just instead of making it 0.75, I could actually do zeros. Well,
Yeah.
I won't give too many of them, but we could do that.
Yeah.
And divide by the 0.05. If you're working it from this division algorithm, which is what we're justifying here, you start the same way. Oops. Yeah. And you move the decimal to the right and 2 to the right. What happens though is this decimal will be indexed up here, right? But then you're still dividing by 5, so you're still saying 7 goes into 5 how many times, right? Or 5 goes into 7 rather, how many times? And then you still have, you're still treating this like 25 divided by 5, so you still end up with the same process. You just end up with a decimal in the whole process. Any other questions on this? Do you remember this division algorithm, this process by which we're doing this? Yeah. Okay, so all of this is hinged on, let me write this down because otherwise you guys won't. So moving decimal points, or moving decimal, yeah, I'll say it that way, decimal points, is multiplying or dividing by power of 10. Here it was that number 100, which is what power of 10? 10 to the second. Okay, so that's where it's related to the 10. Okay. Here's the next one. Okay. What do you guys say? All right, so we're going to talk a little about scientific notation today, okay? Which seems somewhat appropriate because we have a scientist in the classroom today too. So, scientific notation, the basic form for scientific notation is having a number, has some considerations, but that number is being multiplied by 10 to the power. Okay? That number A in the front has some restrictions. That number A has to be between 1 and 10. It could actually equal the number 1. It can't equal the number 10. Between 1 and 10. And it could be a decimal as well. It doesn't have to be a whole number between 1 and 10. And then the number n, the power for the exponent of the 10, actually has to be a whole number. An integer, rather, not whole number, but an integer. So no fractions or decimals in the exponent. There's two different ways we're going to move in and out of scientific notation. One is moving into scientific notation, so taking a standard numeral, one of our beloved numbers written in the forms that we sort of are comfortable with seeing, and turning it into a scientific notation value. And then there is taking a scientific notation, one that's in this form, a times 10 to the n, and turning it back into one of our, which is both moving in and out. So one of the things that I want you to remember is the part in red. So let me talk about the blue first. So if you're changing one of our standard numerals into scientific notation, you need to take the decimal point and you need to actually locate it so that it gives you a number between 1 and 10. We're going to do an example, I promise. So you can take a number and you're turning it into a number between 1 and 10 so that you create the point A. The next thing you do is you're going to count how many locations you moved that decimal to get it there. Did you move left or right, whatever. Okay, so you're going to count the number of moves that you made to get that to happen. In general, the easiest way, I think, to remember which is which in terms of being a positive exponent or negative exponent is that positive exponents indicate a large number. And by large, I mean something more than 10. Okay? And a negative exponent means a small number, something smaller than the number 1. And if you keep that in mind, you don't have to think, did I move left or did I move right? Did I turn something into scientific notation or out of scientific notation? All I have to remember is positive exponents are big numbers. And I'm using the word big very loosely here, but you've defined what I mean by big, bigger than 10, right? And small exponents, or sorry, small numbers, small being smaller than 1, mean negative exponents. So we can use that same idea to go the other direction then as well. So if you're taking something that's in scientific notation and turning it back into a standard numeral, you want to move the decimal point the number of places indicated by that exponent. That exponent is actually telling you how many places to move something. If it's positive, the number should be getting larger than it was before. Positive exponents, larger numbers. If the exponent's negative, the number should be getting smaller than it was before. Negative exponents, smaller numbers. So we're going to give that a try with those ideas for you guys to refer to. So this is a standard number. It's a number in standard form. What number is that? Somebody read it for me. 298,000. So the first thing I want to do is I want to figure out, in standard form, I'm supposed to have a times 10 to the n. I need to figure out what number I need a to be in this particular example. 2.98. Okay, that's going to be a number between 0 and 10. Between 1 and 10, right? For sure. And the decimal point originally was where? At the very end. I mean, I don't actually see it written in, but it's right here. So if I start at the very end and I count the number of places that I moved the decimal, 1, 2, 3, 4, and 5. I moved it 5 decimal locations, 5 locations, right? So this will be times 10 to the 5th or negative 5th. It is the 5th. Why? It's not getting bigger, getting smaller. The original number I had was a big number. It was never bigger than 10, right? So the exponent is a positive exponent. Everybody with me? Large number, positive exponent. Let's use system that you. Yes, you can. I just don't want to teach it that way because then I have to remember both directions. Did I move it left to get it into standard notation or to get it out of standard notation? Yes. So, and your book may present it from the left-right perspective as well. So if you think of it that way, that's awesome. That'll work. No problem.
So, Dr. Woods, what do? You look at the beginning numbers or look at the 290?
You look at the number in standard form. Yeah. That's a good question. All right, so this, because the number in scientific form, 2.98, is always going to be a number that's between 1 and 10. So you're not going to be able to make that decision based on that number. It's always based on the standard notation. All right, 3 decimal point 2. Okay, so starting with a number in scientific notation, it's between 1 and 10, right? Yes? It's between 1 and 10. Okay, but I actually want the number to not have the times 10 to the negative fifth to it, right? But this negative exponent, or this exponent, is negative, which means will my number be smaller than the one I'm currently working with, or larger than the number I currently have? It'll be smaller because it's a negative exponent, so the number is going to be smaller. So I'm going to start down here with the number as it is. In order to make this number smaller, which direction does my decimal have to move? Left. Otherwise, the number will be getting bigger. So I need to move it left. If I only move it 1 to the left, I'm out of numbers. So what am I going to do? I need a bunch of zeros written over here to give me places in which to move these, right? All right. So I've only moved it 1 place. How many places am I supposed to move it? 5, because this is a 5, right? So that was 1, 2, 3, 4, and 5. So you're going to put a 0 in the decimal point. And then how many zeros do I have next? 4 zeros, and then 3, 2. And that would be the standard numeral related to this. All right, so I know that when I first introduced this, I think it's in Math 1, we talk a little bit about why in the world we use scientific notation. So either from that course that some of you have me there, or just from information you remember for why do we want this notation that looks like 3.2 times 10 to the negative fifth? What's it good for? What's it used for? Yeah, if you have something very, very large, like what? What might be something really large? What's the notation called?
Science.
Something in science, because it's called scientific notation, right? So think about something in science that's really, really large.
Like distance around the Earth.
Sure, distance around the Earth, that would work. What other distance might work? Sure, distance to the moon, the sun, or Pluto, or something, I don't know. Some really large distance, right? I don't want to have to write out a number with a bunch of zeros. That's maybe why I want something that's large. What else in science would mean that I might want the notation where I've got that negative exponent? What might I use that negative exponent for? Small numbers.
Microscopic.
Something that's microscopic might work. Maybe the size of an atom or proton. Something really, really small, hence the word scientific notation, right? So scientific notation is not real helpful for talking about how much money you owe the cashier when you pay out at Walmart. Okay?
Some people are big spenders.
They would get the coupons.
Have you ever seen extreme couponing? That bill gets really high.
It does. So, but the point being, thank you, Megan. The point being that the whole idea behind this has to do with things that are very large or very small. Okay, so this is not something that you use when you go shopping. This is something you're using when we're talking about maybe comparing distances that are really large. Because it starts to look an awful lot like the words billion and trillion are the same amount of money, and they're not. Okay? This kind of stuff. So we're comparing really large and really small items. All right, we have one more problem that we're going to do with scientific notation. This problem looks a little bit different, but what you see first in this problem is you see an operation of multiplication that we talk about in Math 1. So the operation that I want to propose to you is that I'm allowed to move this so that it says 8 times 6 times 10 to the 12 times 10 to the 15. It isn't distributive. Another property. It's the commutative property. The commutative property allows me to switch the locations with multiplication, right? 5 times 2 is 6, 2 times 5. So what I really did is I switched the order of the 6 and the 10 to the 12, right? Okay. So that allows me to multiply like terms, if you will, combine the things that are like. So what's 8 times 6? 48, good. And we've had 10 to the 12th and 10 to the 15th. We've had that idea with exponents back in the last chapter. 10 to the what? 27. Okay, so we've actually done the multiplication now. Are we finished with this problem? Why are we not finished with this problem? Yeah. That number 48 is, say it louder for everybody. It's not between 1 and 10. And if it were in scientific notation, it should be. So what number would I like it to say instead of 48? 4.8. Was 48 a larger number or a smaller number?
Larger.
It was large, correct? So what am I going to do to that exponent? I'm going to add 1. It needs to become larger than it was before. If I were making it smaller, I would be subtracting 1, right? I'd have a smaller number to start with. So this would be 4.8 times 10 to the 28. My solution. All right. Let's go on to a different topic here. Rounding. Who's rounded before? Good. A few of you have. That you all have. So there's actually more than one way to round or to estimate. One way of estimating is rounding. So we have the idea of rounding to the nearest, and the reason there's a blank here is because we usually have the word hundredth or tenth or thousands or something like that. It tells you what place to round to. And anytime we're working on rounding, we're looking at one place value beyond what number we're supposed to be rounding to, and it tells us whether we round something up or round something down. And so you guys know the 0 to 4 means you round down, and then 5 to 9 means you round up. All right, so front-end estimation, however, is another type of estimation that you might not have seen before, and it is not rounding the way that we just talked about. Okay, that's a common misconception, is that somehow that they're the same thing, and they're not. Front-end estimation means simply looking at the first value or first couple of values, depends on how much you're rounding to or wanting to estimate to, and rounding off. So rounding off means taking everything after that number and turning it into zeros. Okay? So for instance, if we have the number 356 and we're rounding to the nearest, write it that way, 100, rounding tells me what would this become? 400. Front-end estimation takes the first number, hundreds place, writes it down, and turns everything else into zeros. So, as you can imagine, sometimes that's fine. Right? If the number had been 302, right, 302, and I rounded it to 300, I'm happy enough with that. If the number had been 399, and I rounded it to 300, I'm not so happy with that. But it is a method of estimation called front-end estimation. So we're going to do an example with that. We're going to do 3 things with this problem. The first thing we're going to do is rounding. The second thing we're going to do is front-end estimation. And the last thing we're going to do is actually perform the computation and see how close our estimates are. Okay? If the problem does not tell you what place to round it to, you get to pick. It didn't tell you what to do, right? So what would be the nicest place to round these numbers to? Tens, wouldn't it? Because then I would go with a bunch of zeros. So if we're going to pick, we might as well pick something we like. So let's actually pick to round to the nearest 10, or to work with the tens. Let me write that in. All right, so part A, rounding. If I round 89 and 47 hundredths to the nearest 10, what do I get? 90. And remember, what I'm doing is I'm looking one decimal beyond, or one place value beyond what place I'm rounding to the tens. So this 9 means I round the previous number up, so this becomes 90. How about the 32? That's 30. And then I can subtract and I get 60. Okay, so that is rounding to the nearest tens. B is front-end estimation. So front-end estimation says I have 89 and 47 hundredths, and what will I write down? 80. All I use is the front end, the very first number, and then everything else stays the same. And how about 32 and 16 hundredths? That's 30. And 80 minus 30 is 50. And now we're supposed to actually do the computation. So a bit of advice, you're welcome to use your calculator to check, but if I ask you to do this on a test, I want to see that you've done the borrowing that would be appropriate to make sense when there is borrowing. Carry. Because just like we talked about last time, your fourth graders are not using a calculator to do this. That's not the point, right? All right. So we're going to subtract this. So I may not have any rounding or any borrowing on this one. So 7 minus 6 is 4 minus 1 is 3. 9 minus 2 is 7. And 8 minus 3 is 5. So 57 and 31 hundredths. So which would have to be closer to this one? A. It doesn't always work out that way though. Sometimes your front-end estimation, once you do the subtraction, actually ends up to be a very good estimate. It just depends on the numbers you're working with. All right. And sometimes your front-end estimation will actually look exactly like your rounding, depending on the numbers you're working with as well. All right, we're going to look at rounding to the nearest blank now on these three. This number is 203 and 651 thousandths, right? All right, so if we're rounding to the nearest 100, what will this round to? 200. Right? Because what I'm looking at is I'm looking at the number just beyond the hundreds place, the 0 and 0 and down, or sorry, 0 through 4 rounds down. How about the nearest hundredth? Which number is in the hundredth place right now? The 5. So I need to decide whether that 5 stays a 5 or whether that 5 becomes a 6. It stays 5. Why? Because the one after it is small, right? It's between 0 and 4. So what will this number be? 203 and 65 hundredths. What is nearest unit? What's the units place here? The 3. So I need to decide, does the 3 stay at 3 or does the 3 become a 4? It'll be a 4. Why? Because the 6 after that value is 5 and that 5 to 9, so it rounds up to it. Rounds the next value over up. Okay. There's one more in this lesson. And let's read it together because it's an interesting idea. A student tries to calculate 999 thousandths to the 10,000 on a calculator and finds the answer to be 4.5173346 times 10 to the negative fifth. The student wonders how it could be that a number like 999 thousandths so close to 1 when raised to some power could result in a number so close to 0. How do you respond?
Well, it's like taking a fraction of another number smaller than 1. So every time you do it, it gets another little smaller and smaller portion as you go forward.
That is exactly right, I take you. So the number decimal point 999. Take it into a decimal that makes sense to your mind first. So Kayla, I think you said the number 1/2. Did you? Or did
Yeah.
I make that up? Okay. So Kayla was using the example of 1/2. When you multiply a number by the number 1/2, what happens to it? It gets smaller. Why? Because the number 1/2 is actually smaller than 1 is why, right? Well, this number 999 thousandths is also smaller than the number 1, correct? So every time I multiply by it, what's going to happen? It's going to get some smaller. And And how many times am I going to do that?
10,000
10,000 times. So I want you to try something with me. Grab your calculator if you have it there with you. If you don't, you can look on somebody else's or you can watch the numbers that are going to happen. So let me write first up what Kayla had mentioned, which is very similar to what I have written down. Whenever you multiply by I don't want to use the word fraction because we'll use the word number. Number smaller than 1. And we're talking about positive numbers here. I'm not going to write that, but that's what we're thinking, okay, in order to answer this question. Your product becomes smaller. And we are doing this 10,000 times. That is, we're doing this multiplication process 10,000 times. So we do expect that it's going to continue to get smaller. Here's what I want you to try, okay? So grab your calculator. We're going to be using the exponent buttons on your calculator. So I want you to consider, just to give yourself some perspective on this happening. I want you to take the decimal that we're talking about, this 0.999, and I want you to square it. Somebody tell me what you get. Okay, does that look right, Lauren? Okay, great. And then what we're going to do is we're going to square that result. And most of your calculators should allow you to just hit the square button again. Square the number you had from before.
0.9960599.
Okay, so what I've got here is actually to the power of 4 now, because I've done it to the power of 2 twice, right? Power of 2 twice is power of 4. We're going to continue this process of squaring this number. You may be surprised. What did you get, Megan?
0.9920279.
79 what?
44.
All right. So Megan thinks we're going to be here a while. Square it again. What do you got? I got all the numbers.
0.8797.
Did we go below 0.9?
Yes.
Oh, we did. Okay, what did it say?
0.879.
It's not even 8.9, it's 879? All right, 879, that's not a very good 8.
797033.
Yeah, I think hers just rounds it.
It's okay. Your calculators are doing fine. I'll keep all the numbers in there, even if they're only displaying some of them for you. Oh, what happened next?
0.77.
Okay, I'm only writing once now. 0.77, what?
404-28189.
Point 5991422 854.
Okay, we'll go one more time. How low are you gonna get?
0.35, 817, 147, 810.
You're still here for a while.
We weren't here that long. It actually, once it starts going down, it goes down pretty quickly. I mean, we make some pretty good jumps at times. And it's because we're squaring. I mean, like, we didn't do this just times to the 7th or something like that. That's not what happened. We multiplied it, we did the power of 2 every time. So this is squared, this was to the 4th power, and this was to this, you know, we did our powers up from there. But this gives you some kind of perspective that it doesn't take as long as you might have thought. So why is it going to be such a small number? We get 10,000 times. So yeah, that's why. Does that make sense? All right.